All right, today we get to talk about antiderivatives and rules for integration. So I'm moving into a totally different chapter now. We've spent most of this class talking about derivatives. So we're going to start talking in chapter 6 about antiderivatives. You might have heard of integration before. Basically, we're going to be using these rules for integration to find antiderivatives. So working our way backwards. So like instead of taking a function and finding its derivative, we're going to be given a derivative and being asked to find the original function. So moving backwards. We're going to evaluate indefinite integrals. So we're going to talk about the difference between the two of those in a later section. Eventually, we will also have definite integrals. But right now, we're going to focus on indefinite integrals. We're going to find general and particular solutions to elementary differential equations. Don't freak out, it's not as crazy as it sounds, and we'll solve some application problems involving integration. So really important stuff today. So hope that you are ready and very excited. You should be really excited. I'm excited. Obviously, I always am, but especially today. All right, we're going to consider first this function f of x equals 4x cubed. Now, what is a function? This is capital F of x. Derivative is little f. Well, if you would imagine the process that you would have to go through in order to get a derivative to be this value, you would have originally started out with this constant multiple that's in front as the exponent. So you would have started out with something like, let's say, big F being x to the fourth. But it could be the case that maybe it was like x to the fourth plus 1, or like x to the fourth minus 5. Any sort of constant that you would have added or subtracted from big F would have yielded this same derivative. So we would say that it could be any x to the fourth plus some constant, because we know the derivative of a constant is 0, and we don't have anything else in here. So that would be where the 0 comes from. Now, the constant could have been 0, but either way, any form, capital F, where you have x to the fourth plus some constant, is going to give you little f being 4x cubed as a derivative. So the way that we would write this in our class is we denote constants with, it's usually just like a capital C. And that's how we would denote the antiderivative. So working our way backwards, we're given a derivative when we're finding the original function. If the function capital F is an antiderivative of little f, this is the case if big F prime is equal to little f. And then, like we were saying before, capital F of x plus c is a family of antiderivatives for little f, where c is any constant. So, I mean, you could have an infinite number of antiderivatives that have a derivative of 4x cubed, because that constant could be any number of infinite number of values. All right, if little f is 6x, and big F, we would have to say, working our way backwards. And by the way, if you're like, do I have to keep guessing and checking the whole time? No, I'm going to give you some rules for this in a minute. But you could say that the antiderivative would be 3x squared plus c. And you can always check this when you bring the 2 down. 2 times 3 is 6, and then x would be to the first power, and c just represents any constant. So the check would be if you just took the derivative of the antiderivative, we'd get 6x, like plus 0. Check. So that's how we know that this works. Okay. Now, a lot of the time, I don't want you to get too hung up on this notation with the little f and the big F. Usually we talk about antiderivatives being denoted by capital Fs, but we're going to be using this symbolism here for integration. So an antiderivative is written as an integral. So this is the notation for an integral. It looks basically, it came from just an S, a capital S, but it's basically just an elongated capital S. And this is the integral of f of x dx equals the antiderivative of x plus c. So if you wanted to write this in English, it would be the integral of f of x dx equals f of x plus c. The integral of f of x dx. Now, the dx is part of the notation, and that tells you the variable with which you're integrating. So you're not really doing much with it, but it is going to be increasingly important to you, especially if you end up taking later calculus classes. It's going to really make a difference that you are differentiating with respect to a certain variable. If you end up getting to partial integration, which I don't think you'll hit in this class, it'll really matter. But this is what the notation looks like. The set of all antiderivatives of f is called the indefinite integral of f with respect to x and is written as shown above. So the indefinite integral is just going to be giving you this family of antiderivatives. When we talk later on about definite integral, for those integrals, we'll actually be given bounds. We'll end up getting numerical answers there, just algebraic expressions. So what this would look like with the two examples that we've already gone over is the integral of 4x cubed dx is equal to x to the fourth plus c, and the integral of 6x dx is going to be 3x squared plus c. So that's the way you're going to answer these. And the plus c is part of your answer. So it's really important that you remember to include that, even though you might be like, yeah, it seems silly. She knows what I mean. No, I don't. I do. But I still want you to write your plus c because it's part of your answer. And if you don't have the plus c, you will get a point off. That being said, if you forget your plus c for every single problem on your test, that really accumulates. But if you get the intro wrong, at least you'll get some partial credit for having the plus c on it. So you'll get that point. That's good. I do have a note here that I like to show to students because sometimes they're really thrown off by this symbolism. Remember that we were talking about a derivative of y with respect to x using this type of notation, dy dx. We've talked quite a bit about that. And in this case, we're talking about that as being the derivative. And here we're talking about the derivative as being little f of x. Where we end up getting this notation, in case this is throwing you off, let's say we multiply both sides of this equation by dx. And then we can integrate both sides of the equation. And you can start to see where some of this comes from. So we have the integral of f of x dx is equal to the integral of dy. Well, the integral of dy is just going to be y because you're integrating 1 dy with respect to y, and the integral of 1, or the antiderivative of 1, will just be y. So we would say that y is the integral of f of x dx, and that's where all this notation is coming from. So in case it's bothering you, that's what we're looking at. All right, let's talk about some really important rules for integration, basic integration rules. Okay, so I want to make sure that we are noting that these are very important. Very important. Remember back in chapter 3, you learned derivative rules. So we're basically going to be undoing those derivative rules to get rules for the antiderivatives. That's what we're going to be focusing on right now. Okay, the first one is just if you have the integral of k dx. Now, k is a constant here. So if we're integrating a constant, if we're trying to get the antiderivative, all we need to do is pop an x onto it because we know that the derivative of kx would be k. So when we take the antiderivative, we're just going to write kx plus c. So k is a constant. If I just have a constant inside the integral, then I'm just going to pop an x onto it to get the antiderivative. And again, always just go back and make sure this checks. So if I was to take the derivative of kx, well, the derivative would just be k. And that's what you're seeing inside the integral. Don't forget your plus c. So an example of something like this would be, like, let's say you had the integral of 2 dx. Well, if that was the case, this would just leave you with 2x plus c. That's it. That one's a pretty easy rule to work with. Even though it seems like a really straightforward rule, I still have students who get really mixed up on it. So all of these take some practice. All right, so the integral of k times some function f of x dx is just going to be, what you can do is you can take the constant multiple out of the integral, and then you can just have k times the integral of f of x dx. So it's kind of up to you. You might come across some problems where the k is not bothering you and you want to leave it inside the integral. But if you find that, like, there's just a lot of noise and you want to pull the k out, that's fine, do that too. So I'll give you an example of what this might look like in a basic integration problem. Let's say you had 3 times 4 cubed dx. Well, we already talked about antiderivative of, oh, I'm sorry, did I say 3 times 4 cubed? I meant 3 times 4x cubed. You can pull this 3 out and say this is 3 times integral of 4x cubed dx. And we already talked about this on the previous page, so we already know that is x to the 4th plus c. Okay, so just take that constant multiple out. Another thing that we could have done at this point is we could have taken the 4 out. There's a reason why I left that for right now, just because I haven't given you this rule yet. We're going to do a bunch of examples, though, with these, so have no fear. This would be your power rule for integration. So we talked about a power rule for derivatives. The power rule for derivative means you take the exponent out front and then you decrease the exponent by 1. We're going to undo that. So what we're going to do here is we're going to take our x, whatever that base is, and instead of decreasing the exponent by 1, we're going to increase the exponent by 1. So we're working backwards. And instead of multiplying by the previous exponent, we're going to divide by the new exponent plus c. And this is for n not equal to -1. We have a special case for that, by the way. If n is equal to -1, you're in this situation where you have x to the negative first, and we have a special rule for that. So I'm going to be reminding you as we go through where if you see x to the negative first, don't rewrite it as x to the n. We're going to use a special rule. Okay, so this would be for something like, let's say we had the integral of 5x to the 7th dx, something like that. All right, I can leave the 5 there, or I can pull it out. I'm just going to leave it. I'm going to increase the exponent by 1 and divide by the new exponent plus c. So we usually don't leave our answer like this. It doesn't really look great. We can just say it's 5/8 x to the 8th plus. And that's how we integrate using the power rule for integration. The next rule is the sum and difference rule. It basically just states that we can take the sum or difference inside the integral and turn it into the integrals separately of the sum and difference. So what that would look like would be the integral of f of x dx plus or minus the integral of g of x dx. So just looking at those as 2 separate integrals versus taking the sum or difference inside the integral. And this would look like, for example, the integral of x to the -2nd minus 3 dx. We could do something like that. And you could really just think about this as the integral of x to the negative second dx. And then you could turn this into minus the integral of 3 dx. And then just integrate them separately. Now, if you're like, why would I do that? You don't have to do that. This would be something that I might do if one of the terms was like a lot more complicated. I might split it off into its own integral so I could really focus on it separately. And in a case like this, you probably wouldn't use this rule. But let's go ahead. We'll use the power rule on this first term. Increase the exponent by 1 and divide by the new exponent. And we have this minus sign in between. And then the integral of 3 dx, well, 3 is a constant. We have a rule for the constant. You're just going to pop an x onto it. Don't forget your plus c. So now, instead of adding a plus c onto both of these, you just need to include the plus c one time. Don't include it twice. I mean, I guess technically it would be wrong, but it's just a weird thing to do. So this would just be negative 1 over x minus 3x plus c. So I'll put a box around this. I know we have a little like sub example section right now. I'll put a box around that one too. Maybe I'll put a box around this one too. The next one is the integral of e to the x dx. Well, I already know that the derivative of e to the x is e to the x. So if we're integrating e to the x and we're working backwards, it's very boring. You get e to the x plus c. Very boring. I don't really have an example for you. I guess we could put like a constant multiple in with it, maybe. Like 4e to the x dx. And that's just 4e to the x plus c. So I'll do that. No big deal. The only time we're going to have to be a little bit more careful with these e to the x's is if we have e to the f of x. So remember that we had a special rule for that with derivatives, where we had to chain on the derivative of the inside function. We're going to be talking in the next section, 6.2, about what to do when we had a chain rule situation for derivatives and how we undo that. So in this section, we won't have to worry about that. And then the last one is x to the negative first power. So this was that special case that we were excluding from the power rule for integrals when n was equal to -1. This one is just going to look usually like this, but it could look either way. I normally would have you take something like this, like over here. Or if you had like 1 over x squared, I'd have you turn it into this. Usually I have you leave this alone if it's that special case. And I think it's because this is more recognizable as the derivative of the natural log of x. But we have to be careful here because now we're writing a natural log out of nowhere. So we have to put absolute value bars around the x. Remember that we can't take the natural log of a number that's either 0 or less than 0. We can only take a natural log for positive values. So whatever this value of x is, remember x represents some number that we don't know what it is. Whatever it is, we have to force it to be positive if we're going to use a natural log with it. So that's why these absolute value bars are here. And don't forget your plus c. So the example that I would have for this would be the integral of 3 over x dx. And what this would look like is you could pull that constant multiple out, and then it would look like 3 times the integral of 1 over x dx. And this would just be 3 times the natural log of the absolute value of x plus c. So those are all your rules for integration that I have for you today. Now we're going to go through a bunch of examples of how to use these rules, and then we'll talk about some differential equations, which is super exciting. So the first example I have for you, and I just have one example that's going in this space, is the integral of, and usually we put parentheses around integrals that contain more than one term so we can be very clear about what's inside the integral. This one is going to be 5x cubed minus 2 divided by x to the 4th plus the cubed root of x plus 7 over x minus 2 dx. So there's a lot going on here. Just like we did when we were learning to take derivatives and we had to rewrite the function first, we're going to have to do that also with integrals so that we can get these to fit our rules for integration. So we're going to rewrite everything first so that it's all set up for us. The first term, the 5x cubed, that can stay. I mean, technically you could take the 5 out and split it up into its own integral, but that's crazy. I wouldn't do that. For the next term, we're going to rewrite the x to the 4th in the denominator as x to the negative 4th in the numerator. For the next term, we're going to rewrite the cubed root of x as x to the 1/3. Remember, when you're converting from a radical to a rational exponent, the index of the radical is the denominator. The exponent on the inside is the numerator. Now, the 7 over x, I'm going to leave that. If you would like, you can write it as 7 times 1 over x, or you can just leave it as 7 over x. And that's because it follows this special last rule we talked about. So I rewrote the 2 over x to the 4th because it didn't have an exponent where n equals -1. But this one is the special case that we talked about last. So I'm going to leave this one alone. And then -2 is just -2. All right, but now let's set up for us to use the rules of integration. So the first term, I'm going to use this general power rule here. Shouldn't be calling it that. That's actually a special rule. But I have this power rule that says that if I just have x to the nth power, which in this case we have x to the 3rd power, I can increase the exponent by 1 and divide by the new exponent. So I'm going to do that now, and that's mixed with the constant multiple rule. So I have 5 times, I'm increasing the exponent by 1 and dividing by the new exponent. Now I can use that same exact rule for this term. However, I need to be really careful here because when I have a negative exponent, when I'm increasing the exponent by 1, it's becoming less negative. So just like you did with derivatives, you have to be really mindful of which direction you're heading in. So the -2 is the constant multiple, and then we're going to increase the exponent by 1, which means we're going up to -3 and dividing by the new exponent. We're going to have a little simplifying to do here, which is fine. All right, as far as your third term, again, you're going to increase the exponent by 1 and divide by the new exponent. You're going to find that that power rule is one you would just use all the time. So 1/3 plus 1 is 4/3. When I divide by 4/3, I'm really going to be multiplying by the reciprocal, but we'll worry about that in the next step when we simplify. As far as this second to last term, I'm just multiplying by 7 the antiderivative of 1 over x, which I know is the natural log of the absolute value of x. Do not forget your absolute value bars. And then minus. And then for the last term, when you just have a constant, you're going to plop an x onto it because the derivative of 2x is 2. Remember, you're working in reverse. Once you're at the end, put a plus on there. If you answered like this on a test, I would be like almost completely happy. But this needs to be simplified. It looks terrible the way that it is. Let's go through and simplify. Combine this 5 and 1/4 as 5/4 x to the 4th power. So the 4 stays in the denominator. Now you have a minus, a negative. So we're going to write this as plus. And then it's kind of up to you. No matter what, the 2 stays in the numerator, the 3 stays in the denominator. But I would rewrite any negative exponents as positive exponents. Usually you leave an answer the same way that the problem was given to you. So I'm going to write this as 2 over 3x cubed. Okay, now when you divide by 4/3, you're multiplying by 3/4. So you're going to rewrite this. And you guys are going to get really quick at working on an integral like this and just automatically saying, all right, I'm increasing the exponent by 1, so it's 4/3, multiply by 3/4. And then 7 times the natural log of the absolute value of x minus 2x plus c. It's done. Using basic rules for integration. Wonderful. Wonderful. I have some more examples for you. Of course I do. I'm going to put 3 examples on this page so that you have an idea of how your spacing needs to go. All right, the first one, and these are all illustrating really important concepts. This one is the integral of the square root of x times the quantity x squared minus 1 dx. Now I want you to think back to when you were first learning about derivatives and you were told specific things, like you can't just take the derivative of a product by taking the derivative of each factor and multiplying them together. We had special rules when we took derivatives of products, and we had special rules for derivatives of quotients and for derivatives of composite functions. You're going to find that with integration, we have even more specific rules. So this is a situation where you absolutely cannot take the integral of the square root of x dx and multiply it by the integral of x squared minus 1 dx. You cannot just integrate the product. It doesn't work like that. We're going to have to simplify first. This is like a big no. Simplify it first. When I do that, I know that the square root of x is x to the half. If you would like, write it as x to the half if you find that to be easier. And then to rewrite your integral, remember that you're going to have to distribute here. I'm going to multiply x to the 1/2 into each of these terms. When I multiply with the same base, I add the exponent. So this is really going to be x to the 1/2 plus 2 minus x to the 1/2 dx. I'm going to be very careful to make sure we're using our algebra rules correctly. 1/2 plus 2 is 5/2. So this is really the integral of x to the 5/2 minus x to the 1/2 dx. Now I can integrate. So just like with taking a derivative, I can't just willy-nilly start taking derivatives. I have to get it set up so it matches the rules that we have. Same idea here. Now this is set up to use the power rule in both cases. So I'm going to go ahead and I'm going to increase the exponent by 1 and divide by the new exponent. So 5/2 plus 1 is 5/2 plus 2/2, which is 7/2. So this is going to become x to the 7/2 divided by 7/2 minus, and now I'm going to increase 1/2 by 1, so I'm going to get 3/2. So x to the 3/2 divided by 3/2 plus c. And we're going to rewrite this. By the way, notice that I keep the integration notation on here until I actually integrate. And then once I integrate the function, I remove the notation. So I've seen students who just hang on to this integration symbol all the way to the end. It should not be included on your integral. Once you integrate, the notation goes away. So I'm going to turn this into 2/7 x to the 7/2 minus 2/3 x to the 3/2 plus c. Next one. All right, number 3. This is another one that is special that we're going to have to rewrite before we integrate it. I'm going to give you a big fraction here. In the numerator of the fraction, I have 8x to the 6th minus 2x to the 4th minus 4x squared plus 3 divided by 2x cubed dx. Now, you might not remember this, but when we were talking about taking derivatives for functions that looked like this, again, we said, why would you use the quotient rule? That would be crazy. We don't have a quotient rule for integration, by the way. But we went through this whole process of dividing by the monomial. We're going to do the same thing here so that we can simplify this to give us something that we can actually integrate. Remember, this does not equal the integral of 8x to the 6th minus 2x to the 4th minus 4x squared plus 3 dx divided by the integral of 2x cubed dx. This is a big no. Okay. Does not equal. No. You cannot do that. You cannot just integrate the numerator and divide it by the integral of the denominator. Don't do it. Okay. So let's go ahead and simplify. I'm going to rewrite the integrand. So I'm going to take it out of the integral notation so that I can work on it a little bit, and then I'll put it back into the notation when I'm ready to integrate. Sometimes we just don't want to carry around all these symbols. So what I'm going to do is, since I have a common denominator for all these terms, I'm going to take each one of these terms and divide it by that common denominator. So we're kind of like unsimplifying it right now. So I'm going to rewrite each term separately so that I can use the integration rules that we know to integrate. So 8 divided by 2 is 4. X to the 6th divided by x cubed is x cubed. Remember, if you're dividing with the same base, you subtract the exponents. Then I have minus 2 over 2 is 1. And then I just x to the 1st power. 4 minus 3 gives us 1. Then we have minus 2 over x. And if you're wondering, like, why don't we just write that as x to the negative 1st? Well, it's that special rule for integration where we just have x to the 1st power in the denominator or x to the negative 1st power in the numerator. So I like to leave that one. But this one we'll write as a negative exponent. So this will be plus 3 halves times x to the negative 3rd power. So this is going to be the new integrand. Once it's simplified, if you'd like, put the notation back on it. Now we're ready to integrate. So maybe I shouldn't say equals. Maybe I should have like arrows being like, okay, this leads us to this. Go ahead and integrate now. Okay, so we're ready. All right, so I'm going to increase the exponent by 1 and divide by the new exponent. The 4 is a constant multiple. For the integral of x, when I increase the exponent by 1, it's going from 1 to 2. So this is going to be x squared divided by 2. It's a pretty common one that you're going to see. For the next term, I just have x in the denominator. This is going to be twice the natural log of the absolute value of x. And then for the last term, we're going to increase the exponent by 1 to get us to the negative 2nd power. And we'll divide by that exponent, which is negative 2. And then all we have to do at that point is simplify. But this is officially the integral. Now we'll simplify. 4 over 4 gives us 1. So we have x to the 4th power minus 1/2 x squared. Personally, I feel like this notation's better, but that's up to you. You can always leave it like that. Minus twice the natural log of the absolute value of x. And then here I'm multiplying a positive by a negative, so this term is going to become negative. So I have minus 3 over positive 4, and I'm just going to bring that x to the negative second down to the denominator, plus c. Okay. Remember that you can always check this to a point. Like, for instance, I can check my antiderivative to make sure I get the derivative back, and that will work for you in all of these terms. But getting back to the original problem, you'd have to kind of work your way backwards. So anyway, we'll do one more on this page. So number 4, we have not talked a lot about exponentials, so let's do that now. This is e to the negative x times e to the 2x minus e to the x dx. I probably put in an extra set of parentheses there that's making this look worse. Sorry. Oh, and I left my whiteout downstairs again. You know, we're on the last chapter. I'm never going to learn. By the time I finally get to the last video, I'm going to have everything exactly where I need it and perfect, and I won't need to make any more videos. So, such is life. All right. Remember we said that we cannot just integrate over a product of functions. I'm going to have to simplify this by distributing. So let's go ahead and say we're going to distribute here into the parentheses. When I do that, when I multiply with the same base, I add the exponents. So this is going to look like e to the negative x plus 2x minus, keep the same base, add the exponents. And then we'll simplify. So negative x plus 2x is x. So I have e to the x. And then negative x plus x is 0. Well, e to the 0, any real number to the 0 power is 1. So I can rewrite this integral as e to the x minus 1 dx. Now it's ready to integrate, and this is actually a really straightforward one. I know that the integral of e to the x is e to the x. The integral of 1 is just 1x. Don't forget your plus c. Okay. Wonderful. I have one more for you on the next page, and then we'll talk about these differential equations and initial value problems. All right, this one is the integral of 1 over x plus 1 to the negative second power dx. And if you're wondering, like, why did she write it like that with a negative exponent in the denominator? That was crazy, right? Right, so the whole idea is I need to move everything up. At this point, there's nothing we can do with this. I want to remind you that you can't just look at the denominator and say, well, how about I just increase the exponent by 1 and divide by the new exponent? You can't do that. It's in the denominator, not numerator, first of all. And second, this is all being taken to a power. So we're going to have to rewrite this quantity. I'm going to rewrite this quantity as a positive exponent. When I move this up to the numerator, I just get x plus 1 to the positive second dx. All right, couple things here. First, again, I cannot just increase the exponent by 1 and divide by the new exponent. That's not going to work here because I don't just have x, I have a quantity. So what I'm going to need to do is I'm going to need to square this. And we did this with derivative rules also. Just a reminder. I'm also going to remind you, because students love to do this, all levels of students. I have Cal 3 students who do this. I'm going to remind you that x plus 1 quantity squared does not equal x squared plus 1 squared. Please don't do that. You cannot distribute the exponent into terms. Oh, okay. I'll do this. It's a big no. It was once dubbed the terrible awful. You know who dubbed it the terrible awful? My Calc 2 students who still do this all the time. Don't do that. You're going to have to square the quantity. You're going to have to actually square it. So that means FOIL. X squared plus 2x plus 1 dx. Now you can integrate it. Notice if you just did this, you'd be missing that middle linear term. All right, so I'm going to increase the exponent by 1 and divide by the new exponent. Here, I'm going to do the same thing. Technically, I still have that 2 on there. And the integral of 1 is x, because the derivative of 1x is 1, plus c. And then we'll just simplify this. So the 2's will cancel, and you'll have x squared and plus x plus c. Terrific. All right, let's shift gears here a little bit. I mean, we're still going to be integrating, but we're going to talk about something called an initial value problem and a differential equation. All right, so I'm going to go through this example with you step by step, and then we'll do another one that's a little bit less broken down. Okay, so we're going to let f prime, the function's derivative, be 9x squared minus 4x plus 5. So an example of a differential equation is an equation with derivatives in it. So there's that. What we're going to do is find f of x. So I know f prime, I want to find the original function. Now, A, find the general solution. So that means find the original f of x, including the plus c. Okay, so that'll give us a general solution. We already talked about the fact that you could have any sort of constant being added on to the end of your function. When you take its derivative, it's going to zero out. So the general solution for this particular derivative would be when we took the integral of the function, we're going to integrate 9x squared minus 4x plus 5 dx. We're going to come up first with the general solution. I'm going to increase the exponent by 1 and divide by the new exponent. And we're going to include this plus c. So now we can say that we have f of x is 3x cubed minus 2x squared plus 5x plus c. That's our general solution. Now, the idea here behind the initial value problem is you're going to be given an initial value, like something about the function at a given value, and that's going to help you to solve for c. So for part B, we're given f of -1 equals 0. So you're going to be given 1 point on this family of curves. It's a whole thing. We'll look at it in a minute. But we're given 1 point, and for that we need to find a particular solution. So what we're going to do here is find our function f of x with a particular number instead of c. instead of C. So we'll say that, for instance, in this case, we know that f of -1 equals 0. What I'm going to do is I'm going to take my f of x function and I'm going to find f of -1. So I'm going to take this function and I'm going to say, all right, f of -1 equals 3 times -1 cubed minus 2 times -1 squared plus 5 times -1 plus c, and that equals 0. So this is where we're coming up with f of -1 equals 0. Got it? So here's f of -1. You know, I know maybe this looks weird because it has two different equal signs in it. But if you want to ignore that, fine. We can just only look at this. F of -1 equals 0. I don't have my white out, so clearly I need to just get one that I keep up here. But I usually write it like this anyway, so that's fine. All right, so let's solve for C now. -1 cubed is still -1, so I have -3. -1 squared is +1, so I just have -2 now, minus 5 plus C equals 0. And now I'm going to solve for C. So this gives me -5 minus 5, which is -10, plus C equals 0. And that means that C, when we add 10 to both sides, is equal to 10. So what we're finding now is a particular solution that matches this situation. So what we're going to do is we're going to go back to our original f of x that we found, that general solution. And instead of using C, we're going to use the value that we found for C, which is 10. So our particular solution for this situation is f of x equals 3x cubed minus 2x squared plus 5x. And instead of plus C, we're writing plus 10. So this is the particular solution. So these are kind of fun. I do have my calculator in here if you wanted to look at this crazy graph. Okay, so the idea here behind this, yikes, is that I have this family of solutions that can pop out of here. So like, let's say 3, what is she doing? 3x cubed minus 2x squared plus 5x. And then because I have a plus C, that basically means like it could be any number. So like, let's say I said like, ooh, I don't know, maybe it's +1. And you can do this over and over and over again and create basically this family of curves. Plus 5x. You could say maybe C is -1. Notice how as you start to graph these, okay, so that was the +1 variation that I had. This is the -1 variation that I had. You're going to see you get all kinds of curves. Minus 2x squared plus 5x. Let's say if we were like, I don't know, maybe it's +5. These are all just curves you could have generated based on different values of C, but none of these curves contain the point -1, 0. So what we're looking at here is that we've got a point at -1, 0. Well, notice if you go to your table and you let x be -1, none of these have y values of 0. But now if I use the particular solution that we found, 3x cubed minus 2x squared plus 5x plus 10, that was our particular solution. When we graph that, you're going to see now that our new curve does indeed cross this point at -1, 0. When you go to your table, you're also seeing that function that we graph does indeed have a y value at 0, x is equal to -1. So you're going to get this family of curves, and they're all just basically going to be shifted away from each other. I mean, all this plus c does is just shift the function up and down. So this plus 10 just got shifted up so that its y-intercept was sitting at 10. But this family of curves, I wonder if we could make this look nicer just by fixing our window a little bit. I don't know, to like -3, +3. And then maybe taking our y's out a little more. I don't know. Just trying to help it look better for you. Okay, so that was the +1. This one is the -1. Oh, it's beautiful. I have no regrets. This one is the +5. Here comes our solution, +10. Oh, yeah, I have no regrets. This is beautiful. This is just the family of functions this is a very, very small subset of general solutions. But what we ended up isolating was this pink curve. Sorry if it doesn't look pink to you, but this one is the one that goes through 0, 10, or -1, 0. It contains both of those values. But the whole idea here is this just gives you a family of curves, this general solution, and you're using a particular solution to narrow in on which actual curve is your solution. And it's this pink one, your particular solution. Oh, it's very soothing for the soul. Don't you feel the same way? No? Yes, you do. Of course you do. You know, it's funny because I'm wearing a Peloton shirt right now, but I was just thinking of one of those sayings that one of the instructors has, which is, you don't have to, you get to. And I like to remind my students, like, no one's forcing you to take calculus. This is actually a privilege. A lot of people in the world would probably really appreciate the chance to go take a college calculus course. I know it doesn't seem like that to you, but this is a privilege. You don't have to, you get to. Enjoy it. Sit back and enjoy it. At least, you know, if you try to like it, have a better time. All right, let's see. Find f of x. So I'm going to give you the derivative f prime. F prime of x is 1 plus e to the x plus 1 over x. And then the particular solution, or the value that I'm going to give you, is f of 1 is 3 plus e. We always need more practice with our exponential function, so this will be a good one for you. So what we're going to do first is we're going to integrate to get a general solution, and then we're going to use this value to find a particular solution. Let's go. All right, so f of x is equal to the antiderivative of 1 plus e to the x plus 1 over x dx. When I integrate this, I get x plus e to the x plus, and remember this was that special case where you have x to the n, where n is -1. So this is our natural log of the absolute value of x plus c. This is your general solution. This word general reminded me, I was going through this joke book with kids. The joke was, where do generals keep their armies? And the answer was, in their sleeveys. And at first I thought my son read it wrong. I'm like, doesn't make any sense. Then I realized, where do generals keep their armies? In their sleeveys. And then it became funny to me now. Every time I see general, it reminds me of that. So you can use that. It's not mine. I didn't write it, clearly. All right, that's our general solution. Let's go ahead and use this point to find a particular solution. So what I'm going to do is I'm going to find f of 1, and I'm going to set it equal to 3 plus c. So let's try this new notation here, because I tend to use the two equal signs, and maybe that's throwing people off. So I'm going to use this. So that means I'm going to take f of x. Oh, I've already screwed up my notation here. I mean, it says f of x, but all right. So f of 1 is going to be 1 plus e to the first plus the natural log of 1. Now, if you're evaluating the natural log in a number that's already positive, you can officially drop the bars. It's a little bit redundant. You don't have to force a positive number to be positive. It's already positive, but that's up to you. I don't want you to be confused. Plus c equals 3 plus e. All right, so this is f of 1 equals 3 plus e. That was our condition. Now remember that the natural log of 1 is 0. That usually makes life easier for you. Now we can say that 1 plus e plus c is 3 plus e. And now we can solve for c. So c is 3 plus e, and then subtract 1 and e from both sides. And e minus e is no e's, and then you have 3 minus 1 is 2. Once you found that value for c, you can go ahead and rewrite your value, your function f of x. This time, instead of writing c for your general solution, you're going to use the value of c that you found. So I'm going to rewrite my function as x plus e to the x plus the natural log of the absolute value of x plus 2. All right, so that is the particular solution. We're going to use this idea now to solve a couple of application problems. I have parts A and B for 2 examples, and then we'll be done. It'll be like nothing happened at all. Like it'll be over in no time. All right, the first one is the velocity of an object thrown from ground level is given by v of t is equal to 2t plus 10. Oh, I forgot. This is like the super light marker that should be used to just highlight things. Okay, 2t plus 10. Find the object's position at any time t. So you're being given the velocity, and we need to go back to the position. So if you don't remember these problems, you haven't really seen very many of them since, I want to say it was chapter 3, but maybe you did see some of them in chapter 4. Remember that velocity is the derivative of position. So if I'm given the velocity and I want to get back to the position, then I need to take the antiderivative. So let's go ahead and say s of t is the antiderivative or the integral of v of t. So we have a couple different things to do here, but first let's focus on just finding that antiderivative. So to do that, I'm going to integrate 2t plus 10 dt. Now, I've been throwing these dt's in here, and you might be like, oh, well, wait, what's she doing? We've only been talking about x's. But this is a function t. So we're going to have to integrate with respect to t. So anytime you have t inside your integral, you're going to make sure it's integrated with respect to that variable, if that's what you're supposed to be doing. Okay, so let's go ahead and integrate. When I increase the exponent by 1, I'm going to get t squared. When I divide by the new exponent, I'm going to be dividing by 2. So the 2's are going to cancel. So I'm going to get t squared plus 10 plus 10t. Let's see. Now, remember, you can always go back and check. The derivative of t squared is 2t. The derivative of 10t is 10. Now, we're supposed to find the object's position at any time t, but this is not going to tell me much because there's still this plus c here that's in question. We're going to need a little bit more information, like maybe a particular value, in order to zero in on the actual position function. It doesn't help us much to say that the plus c is in there. But what we can do here is we can think about the fact that the object was thrown from ground level. If it was thrown from ground level, then its initial position, if you want to think of position as height, is 0. And the way that we would write this would be that the initial position, s of 0, so the position at time t equals 0 is 0. So t equals 0 is the initial position. The position itself is 0. The initial position happens at t equals 0 is 0. So that's where the 2 zeros come from. So don't be thrown off by wait, which one's which? Are they the same thing? If I know that, that's all I really need to do in this case to help me to solve for c, because I know that what I just found was s of t. So now I'm going to use the fact that s of 0 equals 0. And I'm going to take my s of t and I'm going to evaluate it at 0 and set it equal to 0. So everywhere I see t, I'm going to substitute it with 0. 0 squared plus 10 times 0 plus c equals 0. Well, not that interesting, right? But sometimes not that interesting makes us happy because it means less work for us to do. Did I just say that? Terrible. What a terrible thing for me to say. I'm just thinking about it from your standpoint. So the position of the object at any point in time t is given by t squared plus 10t. Now we're going to use this to find the position 2 seconds after it's thrown. Now, when you're being given altitude, remember we think generally of the position as being like a height. So in this case, you can think of the altitude as being its height or its position. And then if we're looking at 2 seconds after it's thrown, that means t equals 2. So we're looking for the position at t equals 2. That means we just need to find s of 2. So that means we have 2 squared plus 10 times 2, just using the position that we found in part A, which is 4 plus 20, which is 24. Oh, you don't have any units here. I know, normally I would be yelling at you, like, why didn't you put a unit on this? We'll say the velocity is in feet per second. That means your position would be 24 feet. All right. You have more, one more in you? One more? We have one more. The two-parter. One more, yes. All right. A car decelerates a constant rate from a speed of 90 feet per second, and it does this in 10 seconds to a stop. There's like a lot of information you were just given here, so I'm going to help you parse this out. All right. So first of all, we're talking about how quickly the velocity is changing over time. So if we're decelerating, that's a change in the velocity. Remember that the acceleration a of t is v prime of t. And this is the rate of change of the velocity over time. And we're going to make a little graph here so that you can see what this is looking like. Okay, now if I'm talking about the rate of change of the velocity over time, the way that I'm going to think about this is going to have to do with velocity and time. Usually we put time on the x-axis. And in this case, instead of talking about the position on the y-axis, we're going to be talking about velocity. When we talk about its rate of change, that is talking about the slope, which leads us to the acceleration. So the car decelerates at a constant rate from a speed of 90 feet per second. So the speed will be represented by the velocity. And in 10 seconds, it's down to a stop. So at 10 seconds, it stops. At that initial point in time that we're looking at it. So you have to think about, like, the car is traveling along, blah, blah, we don't care. All of a sudden it starts to decelerate. That's what we're focusing in on. This is not going to be to scale, obviously. But this is your 90 feet per second for your velocity, 90, and then 10 seconds is time. So at time equals 0, you were traveling around at a speed of 90 feet per second. And then at time equals 10 seconds, your velocity was 0 because you came to a stop. So the velocity is all the way down here. And since you're decelerating at a constant rate, that means that your slope is constant. The rise over run is constant. It's supposed to be a straight line. I'm sorry. I did the best that I could to make a straight line. I should have just used a straight edge, but I did not. But that's the situation. Now, what we need to do is find this slope, which is actually going to be pretty straightforward to find, so that we can write a function for the velocity, which is what we're being asked to do in part A. So if I need to write a function, I need a point and slope. So I'm going to go ahead and use the slope, and then we'll put this velocity function together. So the slope is going to be the rise over run. And remember, this is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. You can write this however you want, but basically you have 2 points. The first one is at 0, 90, and the second one is at 10, 0. So put these in either order. I'm going to go y sub 2 minus y sub 1 as 90 minus 0. And then, why did I use that as 0.2? I don't know. 90 minus 0 and 0 minus 10. And look at 90 divided by negative 10 is negative 9. And remember that this is just feet per second per second. It doesn't matter. We're just going to put it into our velocity function. All right, so that's the slope of this function. So we're going to go ahead and start to write this out. V of t is negative 9t, and then plus c in this case. So we're going to have to solve for c, which we can do. Honestly, we don't even really have to do much to solve for c. We know, for instance, that when t equals 0, v of t is 90. So we can just go ahead and use that. 90 is the y-intercept. So I would probably just say, I'm wishing that I had my whiteout pen. We need a slope, we need a y-intercept. So here's my slope. The y-intercept is 90. Y equals mx plus b. In this case, it's just t instead of x. There's your b. So that's going to be your function for the velocity. You don't even need to do any sort of calculus for that, although you could by using that initial position. Maybe I should have done it that way. I don't know. To me, I feel like this is just more intuitive than trying to set up an initial value problem for that. All right, part B. What is the stopping distance? In that case, we're talking about distance. Distance is position. Okay, so distance, remember, just kind of relates how far you've gone, and that's your position. So if I'm trying to find position, I always know that position is using S of t. Now, I don't know S of t, but I know V of t. So I can use V of t to find S. So I can say that S of t is the integral of V of t. We did this the previous page, dt. And we'll get some sort of general function S of t, and we'll have to figure out how we can make a particular solution. Right, so I'm going to take the integral of my velocity, which we found in part A, this function right here. And when we integrate, I'm going to increase the exponent by 1 and divide by the new exponent. And then I'm going to plop a t onto the 90 and add c. So this is my general position, general solution. What we need to do now is figure out that value of c that's missing. So we're going to think about the fact that, again, kind of similar to what we did up here, we don't really care what the car is doing until it starts to do that thing in question. So we need to think about the fact that this car, let's see, it's driving along, and all of a sudden it applies its brakes to decelerate. So it went from a speed of 90 feet per second, and then in 10 seconds, it heads to a stop. So what we want to think about in this case is just figuring out like some sort of way to relate this back to the position. So we can say that when the brakes are applied, that's the initial position that we're talking about. And we can just let that initial position be 0, because I need to figure out how far the car is actually going to go at that point. So let S of 0 equals 0 be the initial position. Oh, sorry. When the brakes are applied. So the car is driving along. We don't care what it's doing until all of a sudden it hits the brakes. So that we're going to say like, all right, this is the starting point, and what we're trying to figure out is the stopping distance. So how far it has to go before it actually hits a stopping point. So we'll let this happen. All right, so this is the start of when you hit the brakes at t equals 0. I know, I feel like this can be a confusing concept. That's why I want to keep talking about it. I'm continually saying the same thing over and over again. But the car is driving along, all of a sudden you hit the brakes, and that's when we're going to start to examine the situation. So we're letting the initial position be 0, and then whatever value we find for the position, we'll just see how far the car has gone. All right, so we know S of 0 is 0, so we're going to go ahead and evaluate this function at 0. Equals 0. So using this with that function. And then 0 plus 0 plus c equals 0 means that c equals 0. Now you can get a function for S of t, your position. So this will be negative 9/2 t squared plus 90t. And then what we need to figure out at that point is your stopping distance. So going back to the original problem, the car decelerates at a constant rate of speed, and that it takes 10 seconds for it to come to a stop. All right, so if that takes 10 seconds from the time that you apply the brakes for the car to stop, then let t equal 10. To find the stopping position. Because it took 10 seconds for the car to stop. So after 10 seconds, what is the position of the car? Okay, so this will be what, 100, 900 divided by 2, that's negative 450 plus 900 is 450, and its position, that's going to be in B. Okay, so that one was kind of tricky. There's a little bit more to figure out with that one, but that's it. That's the last one. Next time, we're going to talk about how to use substitution to integrate when maybe you would have needed the chain rule to find a derivative. So we're going to unchain next time. And then after that, we'll talk about definite integrals and area. But that's it for today. Have a wonderful rest of your day. And I hope you enjoy integrating, telling your friends all about your new skills. And how proud you are of your new skills, because it is a cool thing to be able to do. And it just looks cool. Integration looks cool. You really can't argue that. That's it. That's it. I'll see you next time.